This is section 6.3 on the topic of approximation of functions. And I want to start out here by kind of addressing the idea in parallel with a specific example of using this idea presented in this section. So let's start out and think about this step by step. First, we're going to think of letting V be an inner product space, so a vector space with an inner product defined on it. And let vector V be some vector in that inner product space, in that vector space. Let W be a subspace of V, such that this vector V that we talked about is not in W. So the way I'm thinking about it is we have some subspace W, and there's some vector V that's not in W. So for example, one specific case we could think of is letting our inner product space be the space of continuous functions on AB, with the usual inner product we've been looking at, where the inner product of f with g is defined to be the definite integral from a to b of f times g. If we did that, so that's our space of continuous functions, well, we could say w, the subspace within that, could be Pn, the set of polynomials of degree n. Right? That's certain, they're polynomials, so they're certainly continuous on AB. That is a subspace of this space of continuous functions V. So if we did that, then this W, think of this W representing the space of all these polynomial functions. The vector V from our original vector space V, our inner product space, that's got to be a continuous function. Turns out you could let that be a polynomial, but this is more interesting to think of the case where f is not in W. This V vector here is not in W. So in this case, if W is the space of polynomials of degree n, f would have to be some non-polynomial, right? That's continuous on AB. For example, like e to the x. That's continuous on any interval a to b. That's not a polynomial though, so this is certainly continuous. It's in C of AB, but it's not in this subspace W. Then what we want to ask is, well, what vector in W is closest to V? So out of all the vectors I can look at in this subspace W up here, in that subspace W, of all the vectors, which one is the closest to this V that's outside? And visually, what does it seem like? It seems like it should be just the projection of that V vector into this subspace W, which we've seen how to do in specific cases, how to project a vector onto a subspace. So that's sort of what we're thinking of, is this vector that I've drawn, that would be like this W vector that sits in the subspace and is closest to V. Right? By closest, we mean the difference between the two is as small as possible. For this example we've got running here, where we're thinking of the bigger vector space, inner product space, as being C of AB, and the subspace within there being the space of polynomials. Well, what we'd be really asking then, when we ask what vector W in the subspace is closest to V, what we'd be asking is what polynomial function of what polynomial in Pn is the closest to e to the x on this interval over AB. Right, so what polynomial function g in Pn, this is like our W vector over here in the subspace, which one in there is closest to this f that sits outside the subspace but in CAB? Well, how do we find that? That's what I described up here. It looks like all we would need to do is project V onto that subspace W. And remember, we've actually seen a way to do this if we have an orthogonal basis for W, right? We said this becomes pretty easy, actually. We'll get back to that here shortly, but how do we find that vector W? We just project, let me label this, we project the vector V that's outside the subspace onto the subspace. Right? That's what I've got here for my little drawing, at least. That's this W vector. It's the projection of V onto that subspace. Right? That should be the closest thing in W to this vector V that's outside W. So over here, what does that mean? It means, well, let's remind how we do this in general. We project V onto an orthonormal, or orthogonal, I'll just say, we don't actually have to be orthonormal, an orthogonal basis of the subspace, and add the results. We've actually seen this before for the case of Rn. To project onto a subspace, we actually just take the vector and project onto all the orthogonal basis vectors of the subspace. You might remember we used Schmidt to come up with one of these orthogonal bases, but once we had it, we saw that projecting any vector onto that subspace is easy. You just project it onto each of the basis vectors, the orthogonal basis vectors, and add them up. Easy enough. So when we ask what polynomial function g in Pn is closest to f in CAB, well, how are we going to do this? We're going to project f onto an orthogonal basis, or I'll say the orthogonal basis vectors, some orthogonal basis vectors of this Pn vector space, this vector space of polynomials of degree n. And then all we're going to do is take V, right, this in this V we originally started with that's not in the subspace, and we can say that the closest approximation to V in the subspace U is this projection that we've come up with. So we'll say W equals that projection is the closest approximation. We'll see what closest means. It means closest in the sense of the inner product you're working with, right? The distance defined by that inner product is the closest approximation of V using just vectors in the subspace. Oh, switch to U here for some reason. That should be a W. Sorry about that. And we're going to do the same thing over here. We're going to say F can be approximated by a polynomial of degree n. The projection of F onto this orthogonal basis vectors of Pn will give you a vector in Pn, a polynomial of degree n. That is what's approximating F here. So let's go a little bit further and actually see a definition that kind of affirms some of this idea of, right, taking a vector that's not in a subspace, and we're thinking general subspaces, right, not just Rn subspaces, but taking a vector that's outside of here and saying, well, what's the closest thing that is inside the subspace? What's the closest thing in there to this thing that's outside the subspace? Turns out the closest thing is that projection. And we are, just in the same way that projection used dot product in the definitions in Rn, we're going to use inner product to do these projections in more general vector spaces. So let's take a look here and start with the definition of one of these approximations we're talking about, a very popular one. Let C of A be the vector space of functions continuous on the interval from A to B. Let F be an element of C of A B, like we looked at in this example up here. For example, like e to the x, something like that. Sure, that works. Let W be a subspace of CAB, like the Pn we saw above. The function g in that continuous space of continuous functions, such that the integral from A to B of f minus g quantity squared is minimum, is called the least squares approximation to f in W. Well, if you remember that this expression is really just the norm squared of f minus g using the usual inner product on CAB. Oops, messing up here. Right, using that usual inner product here, we're seeing this stuff is really just the distance squared, right? The norm of the difference between f and g, that's the distance between f and g, it's just that squared. And so we're saying the function g that we can put in here to make this difference between our two functions squared, make that as small as possible, we call that the least squares approximation to f. That function g is the least squares approximation to f if it makes this integral as small as possible. In other words, if it makes the difference between f and g as small as possible in this usual inner product space. So what are we saying here? The least squares approximation to f in the subspace W is really just exactly what we were talking about over here. It's the projection of f down into that subspace. Here's our f that's outside the subspace. Project it down into here. This g is what minimizes the distance between g and f if the g has to be in subspace W, in this plane as I've drawn it here. So the g function that satisfies this definition, that is the least squares approximation to f in W, that g function should just be the projection of f into that subspace. Right, I've written it here as projection of f onto that subspace. And we've done these sort of projections in Rn. We're going to see that we can do them, now that we have inner products, we can do them in any inner product space. So we're really just generalizing something we've already seen, how to project a vector into a subspace to get the closest thing in the subspace to that vector. So let's recall a few things to see how to do this. Given subspace U with an orthogonal basis U1 all the way through UM, just the basis vectors of U, the projection of a vector X onto U, I'm thinking of Rn here, is given by this formula. The projection of X onto this subspace is exactly what we described here. It is the projection of X onto each of the basis vectors U1, U2 through UM. If you go back in your notes and check it out, you'll see this is the projection, this formula here, is the projection of X onto basis vector U1. This, by definition, is the projection of X onto basis vector U2, and so on. So this should be a reminder that to project X onto, UN, to find the projection of X onto a subspace, all you have to do is project X onto each of the orthogonal basis vectors of that subspace. It can be any orthogonal basis, but you need to project it onto each of them and add them all up. That's how you project a vector onto a subspace given an orthogonal basis for it. We've seen that before, but now what we're going to see is it's easy to generalize this to more general function inner product spaces. All we have to do is say that the projection of a element f of an inner product space V onto a subspace W that has an orthogonal basis given by G1, G2, all the way up through Gn, it's going to follow the same formula up here, except instead of dot products, we know we need to trade out for inner products. Since we don't know this is Rn, it's not necessarily Rn. So we can't just use a dot product. It doesn't make sense necessarily. So we need to be more general and just say this will be inner product of f with the first basis vector here, G1, divided by, well, norm of this first basis vector. We can still do that. We've seen a norm with a general, norm squared I have here. We've seen how to express norm in terms of these general inner product spaces. The norm in those is just inner product of the vector with itself. Really, a square root would give you the norm, but we want the norm squared, so we don't need the square root. And then just multiply that much times that vector, U1. but I have forgotten we're using G's here now. Right. I am just directly copying what we have up here for the Rn case, now trading out dot products for inner products. G2 with F with G2 over G2 with G2 and G2. That's like this whole chunk here, all the way out till we get to the last basis vector for W, that Gn. Project F onto Gn. And multiply by Gn. And so you can think of each one of these as being the projection of F onto basis vector G. The G1, G2, and so on. All right. So this is how we're going to do it. This is how we're going to find the least squares approximation of a function in one of these inner product spaces. All we're going to do is find really an orthogonal basis. We do need that it's orthogonal to do it as simply as this formula implies. We'll find an orthogonal basis, and we'll see we can just use Graham-Schmidt to do that. And then you've got a nice easy formula that tells you how to project F onto each of those orthogonal basis vectors to get the projection of F onto the subspace W. So let's go through that process in more detail here. To find a least squares approximation to F, so this thing I've described up here, projection of F onto W. To find that least squares approximation function G, that is G is the approximation to F. First, as we mentioned up there, we're going to find a basis for W. Then to make sure it's an orthogonal basis, we can apply Graham-Schmidt. Again, wherever we had a dot product in the usual Graham-Schmidt process, we've seen how to think of projection with an inner product instead of dot product. So we can apply Graham-Schmidt just the same way as we did before, even if we're not working in Rn. And then we can project F onto each of these orthogonal basis vectors of W and add the result to get the projection of F onto W. Right? That's the general process we really want to remember. So I even want to put a big box around this so we know that this is a good general process to think of here. Okay. By the way, why do we call it the least squares approximation? It's because we are looking at squares in this integral up here. It's the square of the difference of F and G that gets minimized. Okay, so this is going to be a big example. Now might be a good time to pause, take a break. I'm going to go through this process for this example. Find the least squares quadratic approximation to f of x equals the square root of x over the interval from 0 to 1. And so I've kind of outlined the solution ahead of time here to break it up into more manageable pieces. We're going to do the first step, find a basis for this subspace, which in this case, since it's a quadratic approximation, we're finding the projection of f onto P2, the space of second degree polynomials, quadratics. Right? So we need, that's like our W subspace, it's P2. We need to find a basis for that. I claim we can do that right away. Right? A basis for P2. That's about as easy as it gets for a basis for P2, right? Any element G in this P2 space can be written as C times the first vector, B times the second vector, and A times the third vector, all added up. So clearly that's got to be a basis for P2. And you can show they're linearly independent very easily too, on top of spanning. Okay, I don't think that should be a leap. I think we've actually talked about that basis before. So I've got that done. Now, next big step, create an orthogonal basis for W using Graham-Schmidt. You can normalize, but you really don't have to as you go. We'll see sometimes that might be pretty useful, but you don't actually have to normalize if you use this formula we have up here. If you did normalize this basis of G vectors here, then notice you'd have the norm of G squared, which is what I have here, norm of G1 squared, that would be 1, since this is a unit vector in that case. The G2 with G2, that'd be a 1, so this formula would simplify down a lot. But so long as you use this formula, you actually do not have to normalize the vectors when you go through Gram-Schmidt. So let's see how that goes, and then we'll get to that last step of actually projecting F onto each of those orthogonal basis vectors that we've created. Let's get to Gram-Schmidt first. Remember, Gram-Schmidt says whatever your basis is, call that these guys maybe V1, V2, V3. You're trying to come up with a set of vectors U1, U2, U3 that are orthogonal but have the same span as V1, V2, and V3. So first step, take U1 and just let it equal your first vector in your basis. So U1 just equals the function 1, the constant function. That's a 0-degree polynomial. U2 says take your second vector, x, and subtract off the projection of that guy onto the previous directions you covered, so U1 in this case. And here we're going to need to use, since these are functions and not vectors in Rn, we're going to need to use what we know about inner products replacing dot products for these projections. This is V2 minus V2 inner product with U1 over V2, over U1 inner product with U1. All multiplied on U1. Right, by what we described up here, this sort of formula for the projection of F onto a vector is exactly what we're looking at when we use those inner products to represent these. Okay, so what do we have? V2, remember V2 is x, minus inner product of V2 with U1. So that's x with the function 1. Over the inner product of U1 with U1, that's 1 with 1, times U1 is just the function 1. So we do have to compute this little inner product, x with 1 and 1 with 1. And remember, these are integrals, right? This is the integral from, in this case, 0 to 1 is our interval, 0 to 1. X times 1 dx. And you can integrate that and you get a half. If I take 1 with 1, I do get 1. So nice enough, that guy actually is a unit vector already. U1 is already normalized. That's kind of nice. So what do we have here? We have x minus x inner product with 1 was 1/2. 1 inner product with 1 was 1. Times this U1 vector, which is 1. Looks like we have x minus 1/2. That's our U2. And what do? Well, moving on, we do the same thing to get U3, the same general thing. We take the next vector in our existing basis, so V3, which is x2, and then we subtract off its projection onto each of the directions we've already covered. U2, I'll do U1 first. And subtract off the projection of V3 onto U2. And so what does this give me? Well, using those projection formulas, this is V3 minus, well, let's write what V3 and U1 and U2 all equal. Remember, kind of running out of space here. V3 is x squared. That's this guy up here. V3 is x squared. So this is x squared, that's V3. minus projection of x squared onto 1 minus the projection of x squared onto u2, which was x minus a half. The notation's getting kind of clunky here. Let me make some space. The projection of x squared onto x minus a half, because x minus a half was u2. And we just go through this, right? This is some integration here. Got to remember these projection formulas. And that all gets multiplied by x minus a half. And what do we end up with? Let's take a look here. I'll do some integration on the side. X squared inner product with 1 gives me integral from 0 to 1 of x squared dx, right? Times 1 is still that. I get a third. One with 1, we've already seen that's 1 over here. X squared with x minus a half. That's the integral from 0 to 1 of x cubed minus 1/2 x. Just multiply these guys inside. And what do I get? I think here I get 1/4 minus 1/4 is 0. Well, that's kind of nice. That means I actually don't have to finish up this. This whole thing is 0, meaning it zeroes out this guy. But just for good measure, let's go ahead and finish up and see what the norm of x minus a half is. By taking its inner product with itself. I just want to see what this is in case we need it later. It looks like when I plug all this in, at the top bound I get 1 over 24 minus a negative makes plus 1 over 24. So 1/12. Okay. So I think we've computed everything we need and a little bit more. Let's go ahead and plug this in here. Remember you had a minus here. Got kind of buried. We've got u3 is x squared minus inner product x with 1, that was a third, over 1 times 1, which is just 1/3. And all of this whole mess here went to 0 because this inner product x squared with x minus 1 was 0. That means x squared and x minus 1, sorry, x minus a half. I keep saying x minus 1. X minus a half here, sorry. Those must be orthogonal in this inner product space because they have an inner product of 0. Anyway, let me delete that. It's extra. Okay. So we have it. There we have it. Our u1, u2, and u3 make an orthogonal basis for the set of second degree polynomials. So let's gather those up. Remember, u1 is 1. Let's just write this as a set. And I did not normalize. To normalize, I would have to divide each of these u vectors by its own length, by its own norm. You'd have to go through this inner product sort of norm here. But I'm not worrying about normalizing. I'm just finding an orthogonal basis. 1, x minus a half, and x squared minus a third. There we have it. We have an orthogonal basis for this vector space. Now that was a big step. That's one of the bigger steps here. But we see it's just Gram-Schmidt applied using inner products instead of dot products. So the last step here to finish up finding this least squares quadratic approximation is to project f onto each of these orthonormal, actually not orthonormal, we didn't normalize, these orthogonal basis vectors of the subspace P2. And then we'll add them all up to get that projection, right? We're doing this. We are doing this. So far, what we just found that U1, U2, and U3, those were like our G vectors, that orthogonal basis of the subspace, P2 in our case. Now we're going to project f onto each of them with these sorts of formulas, add it up to get that least squares approximation of f, approximation to f in W, this projection vector. So let's do that last step. Let's project f onto each of these guys. I suppose let's remember what f is here, square root of x. So all we have to do is say f, remind us, is this. So we need the projection, let's do it here, of root x onto that first basis vector, that's 1. Right, let me write this in a little more detail. We need to project f onto U2. U2 is x minus a half. It's a lot of math, but it never gets too bad, I don't think. And then finally f onto x squared minus a third, that last basis vector. Kind of clunky there. But this isn't so bad to do. We're just following these same sorts of formulas. We take the inner product of the vector with what it's projecting onto over really the norm of what it's projecting onto. Well, let me just write the norm squared, I should say. But let me just write that as inner product with itself, or 1 with itself, times your vector that you're projecting onto, 1. This guy would be root x, inner product with x minus a half, over inner product of x minus a half with itself. So maybe you see why I went ahead and did that up at the previous step. And then we multiply that by that vector we're projecting onto, x minus a half there. So I need a little more space for this last one. I believe that was our last basis vector U3, x squared minus a third. And so that is just inner product of root x with x squared minus a third over inner product of x squared minus a third with itself. Right, that's the norm squared of x of this vector x squared minus a third. And finally multiply that on the direction you're projecting into. Okay, so once we've got all these vectors all together here, all we're going to do is add them up. Add all these projections of f onto the basis vectors to get the closest thing to f in P2 in the space of second degree polynomials. So what do we get? Well, I'm going to do a little bit of mathematics here and magically pop this up on the screen. Well, let me do one step more so maybe you can try this on your own. Remember, the inner products are easy to write down. It's root x times 1, which is just root x. I'll go ahead and say we've already shown this is 1. We've already shown this is, we did that up here, that's 1/12. So let me write what I need here. I have this, that's almost done. This guy still needs to be integrated, right? Multiply these two and integrate. So I get x to the 3/2 minus 1/2 x to the 1/2 all over 1/12 times x minus a half. And I'm just showing you what all these computations require, and then I'll do those briefly off camera. This last one, 0 to 1, looks like I get x to the 5/2 minus 1/3 x to the 1/2 all over this guy times himself here that times x squared minus a third. Okay, so let me compute these integrals very quickly and see what we're left with. It looks like here, this one I get integrating next to the 1/2 gives me 2/3 over 1 times 1. You can check that I got 2/3 for this, see what you get. That means 2/3 over 1 times 1, that's still 2/3. My next one, it looks like I get this integral, I get 2/5 minus 1/2 times 2/3. That's 1/3. Yeah, I believe that's correct. So what is this? 6 minus 5 over 15. It's 1/15. So it looks like I get 1/15 over 1/12 times this x minus 1/2. That is 1/15 over 1/12 is 12 over 15 times x minus 1/2. And finally, let's see what we get for this last one. I think I end up with, in the top, in fact, let me just magically do this one. And voila, this is what I get for this top integral. I get that this is 4 over 63. You can double check my work there. And for this bottom integral, I get that this is 4 over 45. Again, check my work there. But so I end up with this stuff here, which I can simplify to 45 over 63. And 45 over 63 pretty quickly, which simplifies to 5/7. I suppose while I'm at it, let me reduce this down 12/15. What is that? That's 4/5. Okay, yeah, here I divide the top and bottom by 9. Yes, that works. Okay, so here we have it. We've got this thing pretty well set up. Now we can just write it out. We have the projection of f onto each of these basis vectors of P2. Right, we've worked these each out. We said before, all we have to do now is add them up to get the projection of f onto W. This is our function g that is the least squares approximation to f in W. So we finalize this stuff real quick and add it up. Projection of f onto U1 was 2/3. Projection of f onto U2 was 4/5 of x minus 1/2. And finally, projection of f onto U3 was 5/7 of x squared minus a third. And if you wanted to, you could expand this out and write this in kind of more in terms of that standard basis for P2. But this, in terms of those orthogonal basis vectors, is what we get, right? This is the closest thing to the square root of x. Out of all second degree polynomials. When I say closest, I mean in the sense of the inner product that we're working with over the interval from 0 to 1. This function will more closely resemble root x compared to any other square root function in the least square sense. This is the least squares approximation to f in P2. Great, that's just a quadratic. That's in P2. Okay, so double check all my work here. There's a lot that can go wrong when you're working these out, so be sure you're very careful with those steps. But that is the process here. Remember, big up here, this process. To find that least squares approximation, you have to find a basis, orthogonalize it using Schmidt, then project f onto each of those orthogonal basis vectors of that subspace, and you will end up with the least squares approximation to f in that subspace. It's just the projection of f onto that subspace. Note that if f is in W, the projection will just be f itself. So let me even make that note here. We described all of this thinking of f not being in the subspace, but there's no reason it can't be. If f is in W, then the projection of f onto W, the least squares approximation to f in W, is f itself, which makes sense. If f is already in here, projecting onto it gives you the same thing again. So it really can happen. We just don't usually think of it that way. So, past this example, let's just wrap up this section with an explanation of Fourier approximation, which is a similar idea just with a different basis, a different subspace that we want to project onto. So approximating this idea of Fourier approximation is the idea of approximating f, a continuous function on negative pi to pi, so that's our interval, with the usual inner product that we've been talking about, just the integral from negative pi to pi of the product of two functions. We want to approximate functions like that are continuous on negative pi to pi by functions in this new subspace t from t of negative pi to pi, which is the subspace of C01, C of negative pi pi, that is wrong. It's the subspace of this space we're starting with that is spanned by these vectors. 1 cosine x sine x, cosine 2x sine 2x, all the way up through cosine nx sine nx. Right? This is a very specific subspace of these continuous functions. And Fourier approximation says, well, how can we approximate f using these types of functions? Right? These different modes of sine and cosine. Well, we're going to skip a lot of the details. That's the basic idea. Instead of projecting onto P2, for example, we're projecting onto a set of this form, these sines and cosines, and a constant out front. It can be shown by this definition of inner product that the inner product of any two different elements in this set here is 0 by this inner product, meaning that any two elements here are orthogonal to each other in this inner product space, right? So if they're orthogonal, that makes it a little easier already to think about how to find the least squares approximation in this subspace T, right? We don't have to run Schmidt. We've already got an orthogonal set of vectors. And you can show pretty easily the norm of each of these things. The norm of that first vector 1 is 2 pi, right? Integrate 1 times 1 from negative pi to pi. You get 2 pi. The norm squared of that guy is 2 pi. It can be shown without too much trouble that the norm squared of cosine of kx for any value of k is pi. And any value of k except 0 is pi. And the norm of sine of kx squared is pi. Meaning it's very easy to actually orthonormalize all these just by dividing each of them by their respective lengths here. Divide the first one by root of 2 pi, because this is the norm squared. You want to divide it by its actual norm. Divide by root 2 here. Divide by all the rest by root pi. So an orthogonal basis for t, which is what we need to easily, in fact, even better, not just, I kind of butchered this word, orthonormal is what I was going for. I wrote orthonormal. Let me fix this. Orthonormal. An orthonormal basis for this space T of trigonometric polynomials from negative pi to pi. What would it be? I'm listing them as G vectors, like we had in this big definition up here. Right? I'm listing them as g vectors, since they are orthonormal, it's going to fit nicely into here. Well, how do we make them orthonormal? By their nature, all these vectors are already orthogonal. Make them orthonormal by dividing them each by their lengths that we already wrote out. Right? They're norms. So we can say an orthogonal, or even better, an orthonormal basis for this t of negative pi to pi is really the first vector divided by its norm, 1 over root 2 pi. The second vector divided by its norm, and so on. Divide all these by their norm. The rest of the norms are all just root pi, though. That makes an orthonormal basis for t of negative pi to pi. Sine. Okay, I won't write out all the details. But that gives us this orthonormal basis for this subspace that we're projecting onto. So let's find, so if we want to find the least squares approximation to f in this, all we have to do is say this is really the projection of f onto each of these basis vectors. Just add it up. So this is f with 1 divided by really norm of 1. Well, let's back up. Remember, we already set up here. Where were we? We already set up here in this formula that we're using, if these g's are orthonormal, if these basis vectors g are orthonormal, then all of these divisions here are just dividing by 1 squared, right? The norm of the vector squared. That's what you get when you take the inner product with itself. But if they're all orthonormalized, all those are just 1s here. So you don't have to do all this division stuff. You just take the inner product times the vector you're projecting onto. So this is very easy now. Where are we? Yeah, the projection of f onto this subspace T is just going to be f inner product with 1 over root 2 pi times 1 over root 2 pi. Right? That's the inner product of f with g naught here times g naught. Plus, and we keep adding up, f inner product with this guy times that guy, and so on. All the way out till you get to the last of these basis vectors, f inner product with, what's the last one, sine of n x times sine of nx. Right. So that's the general formula we're going to follow. This turns out not to be too bad, and in fact, we can write this as, well, let's just go a little further and see how we can write this. So this is how we're going to find this least squares approximation to f in T. This formula will give it to us. So with a naught equal to this first stuff here, that's just a number, right? AK equal to the inner product of f with the kth of the cosine basis vectors, and BK is the inner product of f with the kth of the sine basis vectors, right? Which I've written those inner products just as the integrals that they really are over here. That's all we have is all these coefficients on the cosine, sine, cosine 2x, sine 2x, and so on. It's just these formulas for AK and BK. And so if we put it all together, adding all these things up, it turns out we really just got g of x equals that first one that's kind of out of place, right? Doesn't have a cosine or a sine. But then the rest, what are we doing? We're just summing over all the values of k, where we take the coefficient on that cosine of kx and the coefficient on sine of kx, given as we saw in our formula above by these inner products, and just add those up until we get to the last of those basis vectors, n. Right? We're adding up the projection onto all these basis vectors. When we do that, we call this the nth order Fourier approximation to f, and these coefficients here, a naught, ak, bk, those are called the Fourier coefficients. And this might look kind of familiar from Calculus 2, expressing a function as a sum. If you remember that sort of stuff, it might not be a big surprise that taking more terms, taking n bigger and bigger, actually improves this approximation to our function f. Right? The more basis vectors you cover, the more directions you're reaching out in, potentially the better you can describe f. That's how I would think about it. So when you do that, when you take take n all the way to infinity, you never stop taking more and more basis vectors. In that case, really reminding of Calculus 2, we call this the Fourier series of f on the interval from negative pi to pi. That's what this function is called. There's conditions that you can find. Well, we'll leave it at that. So I don't want to do much with this. I want to do a very nicely cooked up little example. Let's find the third order Fourier approximation to the function f of x equals e to the x on the interval from negative pi to pi. And I'm going to give us a little head start here and use the fact that the integral from negative pi to pi of e to the x cosine kx dx is given by this formula. And the integral from negative pi to pi of e to the x sine kx dx is given by this formula. This is going to be very nice because those integrals are really how these coefficients are defined. Right. So this is going to be easy. If I know what these integrals come out to for my f of x equals e to the x plugged in, I can find my ak's and my bk's. I can find my a naught as well. And then I can plug into this formula for the third order, meaning I'll only go up to k equals 3, third order Fourier approximation to f. So we're going to use these formulas here. Right? These formulas. Let's see what we get. A naught, that's the integral from negative pi to pi of f of x dx, which is just e to the x. Oh, sorry, a naught is 1 over 2 pi times that. Very important. This is pretty easy to integrate. This is 1 over 2 pi e to the pi minus e to the negative pi. How about our others, our ak's in that formula? ak's are given by this formula, 1 over pi times the integral from negative pi to pi of our function e to the x times cosine kx dx. So just multiply 1 over pi out front of this integral. By the way, if you're interested in a good exercise, actually figuring out these formulas on your own is a good exercise, not beyond what you can probably do here. You can probably handle that. Okay, but since we know what this integral comes out to, we know it's just all this stuff divided by pi. Finally, the bk's, remember the bk's up here are just 1 over pi times this integral. Let's see what I get there. It's just 1 over pi times this stuff. Okay, so finally we have all the pieces. We can write down our, remember what we're doing, third order Fourier approximation to this function. Right? All we're doing is filling up this formula. This g function is that approximation that we're looking for. So it's a naught plus the sum from k equals 1 to n. Since we're looking for a third order, we'll go to n equals 3, and we'll just fill in the details here. AKs we know a formula for, BKs we know a formula for. Multiply the AKs times cosine kx, the BKs times sine kx. So we have a naught plus the sum from k equals 1 to n equals 3 of the AK values times cosine kx plus the BK values this should be k squared times sine kx. Oops. It's kind of a lot to write out, but it's never too hard, right, if you break it down into the pieces we have it in. And so let's write out what this actually is. It's a lot worse looking than it really is. Notice I can pull out to the front of everything e to the pi minus e to the negative pi over pi. What does that leave behind? It leaves 1/2 from here. Plus, when I pull all that out of this sum, my pi and e to the pi minus e to the negative pi disappear from both of these. That's a constant independent of k. I can pull that out to the front of the entire sum, out here, and then out even further. So what do I have left inside that sum? Looks like I've got this. And notice what I can do here. There's a lot in common to these two terms inside the sum. I can simplify this a little bit. Looks like I've really got... Well, you could do this from here any way you like. I'm just trying to simplify how I see fit. I think that's accurate. You can check my work there. Flip this to a negative because I only took k powers of -1. It left a single power of -1 here. So I absorbed that and make it a negative, kept my k. I think this is all good. And what do we have? Did I do this right? Yes, over pi. Okay. 1/2 plus, okay, when k equals 1, this is a -1 over 2 times cosine of 1 times x minus 1 times sine of 1 times x. 1 times sine of 1 times x. When k equals 2, I get a positive 1 over 5 cosine of k is 2, so 2x minus 2 times sine of 2x. And forgot the k equals 3. When k equals 3, I get added on to the end of this. Let's see if I can make it work. When k equals 3, I get a negative 1 over 10 cosine of 3x minus 3 sine of, can I fit 3x? Yes. Okay, right off the screen, but that'll work. Okay, so I'll move back over here a little. Looks like I've got 1/2 minus 1/2 cosine x plus 1/2 sine x plus 1/5 cosine 2x. That 1/5 distributes to the 2 to make negative 2/5 sine 2x minus 1/10 cosine 3x minus, and minus make a plus 3/10 sine 3x. So it was a lot to write out, but here we have it. We have taken our original function f of x equals e to the x, and on this interval from negative pi to pi, we're saying we can approximate it by this expression in cosines alone. And in fact, we're saying that this is the closest vector in this t subspace to the e to the x exponential function that we started with in c negative pi to pi. Okay, so I know I kind of cheated here by having a lot of these results from the get-go, but I hope you see why I did that. These problems take a long time, even if you have that. It still took us a long time to write down our final result. But this is the third order Fourier approximation to f on negative pi to pi. Okay, that's it for this video. See more in the next section.